Hello, I'm Kiuchi of Sumitomo Precision Products or SPP. Today, I'd like to talk about commercial production of low-K PZT film using sputtering method. And it is co-authored by researchers at SPP and Tohoku University. Firstly, I will talk about the background. Polycrystalline PZT thin film has been widely used for MEMS devices because of its advantage of the large driving characteristics, which depends on its high D31 coefficients. However, it is not suitable for devices requiring not only the performance of actuator, but also that of sensors such as PMAT, due to its high dielectric permittivity. On the other hand, monocrystalline-like epitaxial PZT film is expected to improve the performance of the device compared with polycrystalline PZT thin film because it enhances the device figure of merit or FOM primarily resulting from reduced PZT dielectric permittivity. However, so far, the epitaxial PZT thin film with both high D31 and low permittivity has not been available on the market because of the trade-off between them. So we have developed commercially available epitaxial PZT thin film on silicon wafers. The PZT film, which have two kinds of composition ratio of zircon and titan. They are MPV and titan rich. By taking into account its impact of D31 and permittivity are demonstrated. In order to characterize the transverse piezoelectric response of the low-K PZT thin film material, a laser Doppler Bible meta measurement or LDB technique was employed. This is a schematic diagram cantilevers with a PZT capacitor for the measurement, and this is a measurement setup. Cantilevers are driven with a peak-to-peak 0 to 30 volt sine wave at 500 Hz. A DC bias of half the peak-to-peak voltage was applied to produce a unipolar drive of the capacitor. Displacement of the cantilever results from the strain induced by the converse piezoelectric effect of the thin film. The LDB system measures the displacement of the cantilever tip. From the cantilever tip displacement and dimensions and materials elastic compliance, the transverse piezoelectric coefficient D31 is calculated. This is the typical 110 pole figure for a 2-micron thick PZT film. The four-fold symmetry of the 110 diffraction shown in this figure confirms the monocrystal-like epitaxial structure of the PZT. The PZT is 001 oriented to normal to the substrate surface and oriented in plane with a cube-on-cube structure relative to the silicon substrate. These figures show typical SRD patterns of MPV and titan-rich films. The C-axis orientation ratio of the titan-rich film is higher than that of MPV film, which was calculated from the comparison of intensities between 400 and 004 peaks of PZT. These results indicate that the permittivity of titan-rich film is lower than that of MPV film because C-axis oriented PZT-based epitaxial thin film has small dielectric constant. This is a 10 cross-sectional image where significant stacking fault was not observed. Because the ferroelectric nature of the PZT hysteretic behavior of the transverse piezoelectric coefficient D31 is expected to and is shown here. The function of the applied electric field. For this plot, the applied voltage shown on the x-axis, the peak-to-peak voltage, and the DC bias voltage is half of the peak-to-peak voltage applied at each point. The measured D31 coefficient is nearly constant over a wide range at the top and bottom of the hysteresis, and the magnitude of the D31 coefficient is nearly symmetric with respect to applied voltage polarity. Consistent with the polarization hysteresis measurements, there is an asymmetry of the positive and negative coercive voltage of the D31 hysteresis. This effective shifting of the hysteresis loop to the left is attributed to a positive internal bias field within the PZT. These figures show the implying uniformity of the D-31 coefficient for several devices cut from a linear array of position across the diameter of a wafer coated with the epitaxial PZT film stack. The ratio of standard deviation and average value is less than 2%, and the uniformity is well enough to use commercially. This table summarizes the characteristics of two kinds of monocrystalline-like epitaxial PZT films. MPB and titan-rich PZT films average piezoelectric D31 coefficient 185 picometer per volt and 149 picometer per volt. And relative dielectric permittivity of 430 and 264, and dielectric loss of 0.015 and 0.020 respectively. Both waveform M derived from the D31 and the permittivity are over 50 gigapascal. This value is more than 40% higher than 35 gigapascal of the world's highest level commercial polycrystalline PZT thin film, and superior to 14 gigapascal and 34 gigapascal of aluminum nitride and scandium aluminum nitride, respectively. This high figure of merit also indicates that the low-K PZT can be beneficial for resonator device designs. For more information about SPP low-K PZT, please contact us. Thank you.